Hello, in this video we'll talk about adders. We'll first introduce a full adder, then we'll move on to parallel adders, a subtractor, and how to design it, and finally we'll implement a full adder using behavioral modeling in Vhdl, and after that we'll implement a parallel adder using structural Vhdl code. The full adder is the basic building block for a parallel adder, and it basically adds 2 bits in addition to a carry in bit and outputs the result of the summation and the carry out bit. So in total, the full adder has 3 inputs, A, B, and the carry in. So A and B are the numbers we want to add, Cin is the carry in. And the full adder also has 2 outputs, the carry out bit and the sum bit. So if we want to fill in the truth table of the full adder, we'll have 2 outputs, the Cout and S. Let's try add 0 plus 0 plus 0. The result will be, of course, the sum bit will be 0 and the carry out will also be 0. The next row in the table requires us to add 0 plus 1, and the result of that summation is 1, and there is no carry out for this addition. That means Cout will be 0. Here we also have just 1 and 2 zeros, so 1 plus 0 is 1 sum bit, 1 for the sum bit and 0 for the carry out. In this or in the next combination, we're adding 0 to 1 to 1. So 1 plus 1 is 2. That means we'll have a sum bit equal to 0 and we'll have 1 carry out. And if you notice, you can read this as a 2-bit binary number whose value is 2, because 1 plus 1 is 2, and in the binary system the maximum value a bit can have is 1. That means we cannot have the sum equal to 2, but instead we chose we assigned the sum value a bit of 0, and we said we're going to have a carry out of 1. This is because, again, the addition of 1 to 1 gave us 2, and 2 in binary is 1 in carry out and S is 0. Here in the next combination we're trying to add, we're adding 1 plus 0 plus 0, so that means we have a sum bit of 1 and no carry out. Next we have 1 plus 0 plus 1, that means the result is 2, so S must be 0 and we'll have a carry out. This is similar to the highlighted case from earlier. We had 2 ones at the input, so the summation resulted in 0 with 1 carry out. Next we also have 2 ones at the input, so 1 plus 0 is 2, so the result will be also 0 for S and 1 for the carry out. The last row in the table has 1 plus 1 plus 1. So we have 3 ones at the inputs. Adding them will of course give us 3 in decimal. So that means we'll have 1 for the sum bit and 1 for the carry out. And again, reading this value as a binary number or as a decimal number, or converting it to a decimal value, will result in the number 3 in base 10, or 3 decimal, which can be written again as 1 1 in the binary system. We can connect multiple full adders to create a parallel adder in this way. So notice how input A is now changed to A0, A1, A2. A0 is the least significant bit, and input B is changed to B0, B1, B2. To create the connection, we have to connect the carry out of the first full adder to the carry in of the next full adder. So Cin at 1, or full adder 1, is equal to Cout 0. We take the carry out of the full adder number 0, connected as Cin to the next full adder, and so on. So Cout of full adder 1 is connected to Cin of full adder 2. And the last carry out will be just outputted as the carry out of the addition, and we'll also have a total of 3 sum bits if the inputs are each including or consisting of 3 bits. The first carry in bit of the parallel adder must be connected to a logical value of 0. And now this is the complete circuit for a 3-bit parallel adder, meaning a parallel adder that is capable of adding 2 3-bit binary numbers. So we have number A, which consists of 3 bits. We have A2 as the highest significant bit, and then A1, and finally A0. The second binary number we're adding is also consisting of 3 bits, and it's variable B. And we can write B as a 3-bit binary number by putting first B2 as the highest significant bit, and then B1, and finally B0. So if we want to add, for example, 2 plus 3, then we have to write A as 2 in binary using 3 bits. So this is how to write 2. And to write 3 for B as a 3-bit binary number, we'll say 0, 1, 1. That means A0 must be 0. So this is A0. All right. A1 is 1. And finally, we have A2 as 0. The same goes for number B. So we'll put 0 for A0. So this will be 0. A1 will be connected to 1, and A2 will be connected to 0. So that means A is equal to 3. A is equal to 2. On the other hand, for the second input of the full adders, B0 must be connected to 1. B1 must be connected to also 1. And finally, B2 is connected to 0. So at the output, when we add 2 plus 3 in decimal scale, we'll get 5, of course. So 2 plus 3 is 5. Doing this addition using binary numbers, we'll say 0, 1, 0, or a 3-bit binary number representation. This is for 2. To add 3, we'll say 0, 1, 1. We can perform the addition just like how we do it using the decimal scale. We'll add 0 plus 1. The result of that is 1. Then 1 plus 1 in binary scale is equal to 0 with the carry out of 1. Because in decimal scale, 1 plus 1 is 2, and we cannot write 2 as a single bit in binary. So we have to say 1 plus 1 is 0 with a carry out of 1. Then we have 1 plus 0 plus 0. The result is 1. And if you translate this number to decimal scale, that will give us 5. So the summation is correct. And we can expect, or we can say that the expected result is S0 is equal to this bit, so it's 1. S1 is the bit in the middle, so it's 0. And finally, S2 is equal to 1. And the last carry out, which can be considered as S3, will have a value of 0. Since there is no carry out at the end here, we can say that S3, or the last carry out, is equal to 0. If we want to design a subtractor, given the knowledge of how to create an adder, we can simply do that by complementing the second bits from each full adder. So in this case it's B, bit B. So we complemented each value of B, and we replaced the first carry in with a value of 1. This will ensure that we get the 2's complement of b, and again this will act as an adder that adds a with the 2's complement of b. That means it will do a plus negative b, and the result will be subtracting a or subtracting b from a, which is basically a subtractor made using full adders. Now here we see the circuit for the full adder. We can refer to the table and extract it from there by creating a key-map and then simplifying the expression. We can write the expression for the full adder from the given circuit as 2 signals or 2 expressions. First one is the summation bit. S is equal to, from the graph or the diagram, we can say that S is equal to A XORed with B XORed with Cin. The second signal is Cout, and we can write Cout as Cin ANDed with A XOR B. ORed with A and B. So now we have 2 expressions, and we know that we need 3 inputs, A, B, Cin, 2 outputs, S and carry out. That means it is possible for us to implement the full adder using Vhdl code, and this can be easily expressed using behavioral modeling. The first 3 lines in our code for full adder .vhd is going to be the library declaration, so we're going to add the 3 lines for that. And then the next part in our code will be the entity declaration. So let's decide on naming the full adder file or entity as entity full adder, and that is again going to be the file name. So it will be full adder.vhd for the file name, and for the entity it will be full adder as one word is and then end full adder. Inside the entity declaration part, we're gonna declare all the ports that are necessary, meaning all the inputs and the outputs for our circuit. And as we mentioned earlier, we have only 3 inputs, A, B, and Cn. So we're gonna say port A, B, Cn, and these are all inputs, so we'll say in, and these are all as well one single bit, so we'll say standard logic. Next, we're gonna put a semicolon and list the outputs. So we only have 2 outputs, S and carry out, so we'll say Cout, S, these are outputs, so out, and these are also a single bit each, so we'll say standard logic. Here, the order is very important for us to remember when we implement any code that depends on the use of the full adder expression. So we'll put A, B, Cn, carry out first, and then S, as we saw in the table earlier, or the truth table for the full adder. The last part in our code is going to be the architecture part. I'll call the architecture behave. So we'll say architecture behave of full adder is begin and behave. And in between begin and end, we're going to write the expressions for each of our outputs using behavioral modeling. We have 2 outputs, S and Cout. Let's start by defining Cout as A XOR B, ANDed with Cn, ORed with A and B. So this is the expression we saw earlier, or we defined earlier, except we translated it into Vhdl code by spelling out the name for each gate rather than using the Boolean symbol. So again, for Cout, it's A XORed B, XORed with B, ANDed with Cn, ORed with A and B, so A and B. This is for the carry out bit. To define the sum bits, we have to trace the lines here. S is equal to, as we can see, A XOR B, XORed with Cn. So we'll say S is equal to, or as assigned a value equals to A XOR B XOR Cn, and don't forget the semicolons whenever they're needed. And now this is the complete VHDL code for the full adder entity. Now what we'll do is design the structural code for the 4-bit parallel adder. For a 4-bit parallel adder, we need 4 full adders, because each full adder is only able to add 2 bits together plus the carry in bit. So the 4-bit parallel adder will consist of 4 full adders connected this way. We can name each full adder uniquely. So we have FA0, FA1, FA2, and finally FA3. Notice how the carry out of the first full adder is connected as the carry in of FA1. The carry out of the next full adder is connected as the carry in of the full adder that follows it, and so on. That's why another name for the parallel adder is the ripple carry adder, because each carry out is connected as carry in of the next full adder. Before we move on, let's emphasize that this parallel adder is capable of adding 2 4-bit numbers, and we can name these numbers A and B. A consists of 4 bits, and we can write these 4 bits according to their significance as A3. So A3 is the highest significant bit, and then we have A2, A1, and finally A0. And we can write the bits for B as similarly B3, B2, B1, and finally B0. Before we decide on what components are needed, what ports and what signals are needed for implementing this using structural code, let's adjust the circuit slightly by relabeling the internal connections. We said the carry in of FA1, or let's say the carry out of FA0, is equal to the carry in of FA1. So we want to give this a single name and repeat that for the rest of the signals. So we'll call this first wire as Cout0, then Cout1, Cout2. And these are going to be our internal signals, since they're neither ports, they're neither input ports nor output ports. So let's start defining what components are needed. Clearly we'll need only one component. That component is instantiated 4 times. So we'll need only one full adder as a component, and then we'll use that full adder 4 times. The signals, or the internal signals, are only 3: Cout0, Cout1, and Cout2. Notice how again A and B all have one name each, but for example A has multiple bits. So variable A is consisting of a cable consisting of 4 unique wires. So A is a 4-bit variable, and the bits of A are 0, A0, A1, A2, A3, A0 being the least significant bit. The same goes for S and B. So we can say that for the ports, we only need A, B, and S, and finally Cout, where A, B, and S are each consisting of a vector of 4 bits. So we can only say again A, B, C, N, Cout, S are our only ports. Of course, A, B, C, N are input ports, Cout and S are output ports. And so far we've only learned how to express if a variable or if a port is a single bit. Here A, B, and S are ports consisting of 4 bits. And the way we can express that is by saying instead of standard logic, we'll say standard logic underscore vector. This specifies that it's more than a single bit. The signal is more than 1 bit. But again, we have to specify how many bits it has. So we'll need to add to this brackets starting from the highest significant bit until the lowest significant bit. For A, B, and S, we need, for example, A0, A1, A2, A3 for A. So the way we express that is by saying 3 down to, as one word, 0. So 3 down to 0 means 4 bits, and there, for example, for A, it's going to be A0, A1, A2, and A3, 3 being the highest significant bit. So let's start implementing the structural VHDL code for the parallel adder. We'll start with the library declaration. We'll need the 3 lines here. Next, we'll explain, or we'll declare the entity that we'll need. We can call it parallel adder. So we'll say entity parallel adder is and parallel adder. We said we'll need to declare the ports, the input and the output ports in the entity part. So we'll say port A, B as a vector consisting of 4 bits. So we'll say AB, port AB in standard logic vector 3 down to 0 because we have 4 bits. And then we'll add CN as an input with 1 bit, so standard logic. We'll put a semicolon now to list the outputs. We'll start with Cout as 1 bit, so we'll say Cout is out 1 bit. Semicolon S is output of type vector consisting of 4 bits, so 3 down to 0, and that's it. We'll close the bracket of the port, put a semicolon. And now we're ready to define the architecture part. You can call the architecture struct. So we'll say architecture struct of parallel adder is. This is an empty template for the architecture part of a structural code. So we'll start by declaring all the components, the unique components that are needed. And we agreed that we need only the full adder as a component. So between component and end component, we're going to mention that we need the full adder. And we have to list the ports of the full adder as they are in the file that we defined earlier. We can simply copy paste that line of code. We'll say full adder port, list the ports of the full adder, so A, B, C, N in standard logic, and then Cout S out standard logic. Next, we have to define the signals that are needed, and we decided in the plan that we made earlier that we need 3 signals: Cout1, Cout2, and Cout0. So Cout0, Cout1, Cout2. And these are each a single bit, so we'll say standard logic. Now after begin, we're gonna start defining the connection between the output and the input of the entity parallel adder. We can refer to the diagram we saw earlier. The diagram has 4 instances of the full adder. We can call them FA0, FA1, FA2, and FA3. Let's start defining FA0 and do the port mapping for FA0. FA0 takes A0 and B0 as inputs, along with Cn, the first carry in, and it outputs in this particular order Cout0 and finally S0. And this is how to extract specific bits from a vector. We call it by its number and we put it in between brackets. Next, we're defining FA0 or FA1. FA1 is of type full adder as well. And then we'll say port map. The inputs are A1 added to B1 added to C out 0, which is the carry out of FA0. So these two values are the same. Let's use a different color. Okay. FA1 outputs C out 1 and S1, and C out 1 goes as the carry in of the next full adder. So FA2 is full adder, port map A2, B2, carry out 1. This is the carry in of full adder 2, which is the carry out of full adder 1. And then we'll continue by placing the outputs of FA2, and these are C out 2 and S2. And finally we have to define FA3, and FA3 is a full adder, and we'll say port map FA3 takes A3 with B3 as inputs along with C out 2 as the carry in bit, and it outputs the last carry out, which is the carry out of the expression, which has to be spelled correctly according to how we spelled it in the ports of the parallel adder. And finally it outputs S3. Now this is the complete code for the 4-bit parallel adder. Thank you for watching and good luck.